Right, okay. All right. Good evening. We'll start. Right, my audio and video is fine, right? Right, so we are in a point where you are 10 days from the exam. Right? So we are in a point where you are 10 days from the exam. Right? And today we are with the day 4, I guess, day 4 of this discussion. Right, and today I'm planning to discuss some electricity questions, right? Electricity essays, right? So especially if you are planning to write electricity essay, right? Write electricity essay, right? Now this session will give you a recall and a complete idea about the tips and tricks that we use when writing electricity essays, right? Okay, then we'll start. Let me share my screen. You can find the questions in the Telegram channel, right? If you haven't got the questions, you can find it. They are in the Telegram. All right. Right. Then let's start without any further ado. Right. Let's start without any further ado. One more second. Live is shared in the groups, right? Okay. Okay. First one. All right. First one. The figure shows a 12-volt DC electrical circuit. 12-volt DC electrical circuit used to detect parameters such as temperature, pressure, and concentration of a flammable gases in emergency situations. It has three separate branches, A, F, B, and CD, as shown. Right, CD as shown. The CD branch includes another 4-volt battery. Rx equals 10 ohms, Ry 15, Rx 10, Rx 10, Ry 15, Ry 15, and Rz 6, Rz 6. Okay. Are the resistance values of the sensors used for detecting three parameters mentioned above, F1, F2, and F3 are mentioned above. That's it. F1, F2, F3 represent three fuses. Assume that batteries and fuses have no internal resistance. The maximum continuous current through a fuse without burning is termed as fuse rating. The fuse ratings of F1, F2, F3 are 1 ampere, 5 amperes, and 2 amperes respectively. Okay. Then part A. Calculate the current I through branch AF. Branch AF, right? Then see, if this is 12 volts, here we have something. If this is 12 volts, now this is a ground in, no? If this is a ground in, say this point is point X, but that is given as F, no? Then this is F. Say this is F now. And this point is given as A. Then potential difference across AF is exactly 12 volts. Potential difference across AX is exactly 12 volts. Now, first question, A1. Question 1, A1. Then calculate the current through branch AF. Then delta V equals IR. Delta V is 12, right? I need I. And resistance is Rx is 10, and 2 ohms is given, then 10 plus 2, 12. Right? Resistance is 12. Then I equals 1 ampere. Right? Second one. If the potential at junction B is VB, okay. Junction B is VB. What are the potential differences between BE, VBE, and CD, VCD. Okay. Now we know these are grounding, no? These are grounding. Then if this point is 0, all these points are 0. They are groundings. They are groundings on the same point. Then VBE, VBE, no? Then we know VBE can be written as, see, VBE can be written as VBE. VBE can be written as VB minus VE. Right? Now, VB is VB minus VE is 0. Right? E is at the grounding, then VB equals VB. VBE equals VB. Right? Then for VCD also, we can write VCD equals VC minus VD. Now here also, VD is also grounding. Right? Then VC minus 0, then VCD equals VC. VCD equals VC. Right? Then VC and VB are also equal. Then we need to keep the answer in VB in terms of VB. Then we can keep the same answer as VB. Right? Because VC and VB are also equal. Right? B and C are on the same wire. Then part 3. Part 3. Hence, write down expressions for the currents I1, I2, and I3 in terms of VB. Right. I1 is across these points. Right. Now, if this is 0, we know then point A becomes 12. If that is 12, this is also 12. Then for RS, if you apply for RS, delta V equals IR, then potential difference is VA minus VB. VA minus VB equals I1 RS. I1 RS. Right? Then VA is 12. VA is 12. Then 12 minus VB equals I1 RS is 2. Then I1 is given by 12 minus VB. 12 minus VB over 2. I1 is 12 minus VB over 2. Right? Then we need I2. I2. Okay. To find I2, first we need the equivalent resistance here. No? Then equivalent between these two is, we know 1 over R equals 1 over 15 plus 1 over 10. Then 1 over R equals, this is 30. Then 2 plus 3. Then R equals 30 over 5, 6 ohms. Equivalent of Ry and 10 is 6 ohms. Ry and 10 is 6 ohms. Right? So if that equivalent is known, between B and C, we know that is VB, no? That potential difference is VB, no? Then for the branch BE, if we apply V equals IR again, for the branch BE, right, then VBE equals I2 R. But VB is VB. We need I2. And total resistance is 6 plus 2, 8. Right? 6 plus 2. 6 plus 2, 8. Then I2 equals VB over 8. I2 equals VB over 8. Right? Then finally, I3, resistances are known. Right? Resistances are known. And total potential difference between C and D is, now we know VC is equal to VB. Then another 4 volts battery is also connected. Right? Another 4 volts battery is also connected. Then what total potential difference should be? VB plus 4. Then for that one, again delta V equals IR. Delta V is VCD equals I is I3, then I3R. VCD can be written as VC is equivalent to VB, right? VC is equivalent to VB, and another battery of 4 volts is connected here. Then total potential difference is VC equals VB, no? Then VB plus 4 equals I3. Total resistance is 6 plus 6, no? 6 plus 6. 6 plus 6. Then I3 is given by VB plus 4 over 12. VB plus 4 over 12. Right? Currents are known. Right? Currents are known then. 4. Considering the currents at junction B, calculate VB. Right, at junction B, okay, we know at junction B, I1 is the inflow and I3 and I2 are outflows, no? I3 and I2 are outflows. Then, using Kirchhoff's first law, we can say, I1 equals I2 plus I3. Right now, I have answers for I1, I2, I3. Plug it here. I1, 12 minus VB over 2. 12 minus VB over 2. I2, I2 was VB over 8. I2, VB over 8 plus I3, VB plus 4 over 12. VB plus 4 over 12. Right. Now have to simplify. By 2, this is going to cancel. Then 2 times 4 and 6. Right. Then 12 minus VB equals VB over 4 plus this is VB over 6 plus 4 over 6. Right. Now we have to simplify. Then this is 12 minus 4 over 6. Right. And from the other side, VB is common. If we take it out, 1 over 4 plus 1 over 6 minus 1. Right. Sorry, plus 1. Plus 1. Then if this common denominator is, now this is cancelling, no, 2 and 3, then if the common denominator is 3, then this is 3 times. This is 12 again 36, 36 minus 2, 34. Right? Then VB, and here 6, 4 means 12 is the common denominator. Then 4 times 3 and 6 times 2, this times 12. Then 34 over 3 equals 12. VB 5, 17. 17. Then 17 and 34 cancels off 2. Then 3 and 12 cancels 4. VB equals 8 volts. Right? VB equals 8 volts. That's it. VB equals 8 volts. A small simplification. Right. 5. Calculate the potential difference across the resistor RS. Okay. Then that is VAB, no? Then that is VAB. VA is known. Then VAB equals VA minus VB. VA was 12. VB is 8. Then potential difference is 4 volts. Right? That's a normal one. Then 6. Using your expressions in A3 and the value obtained for VB in A4 above. Right? A3 and value obtained for VB in A4 above. Calculate currents I1, I2 and I3. Okay. Then I1 was 12 minus VB over 2. Then I1 12 minus VB is 8 over 2. Then I1 equals 4 over 2, 2 amperes. Right? 2 amperes. Then I2 was we found I2 VB over 8. VB over 8. Then VB was 8. 8 over 8, 1 ampere. I2 is 1 ampere. Right? Then I3 was VB plus 4 over 12. Then VB is 8. 8 plus 4 over 12. Then I3 is also 1 ampere. Right? Currents are 2 amperes, 1 ampere, 1 ampere. 2 amperes, 1 ampere, 1 ampere. Right? 7. Calculate the power dissipated through resistors Rx, Ry, and Rc. Rx, Ry, Rc. Okay. Power dissipations. So we know power can be written as, if current is known, I squared R. Right? Then for Rx, say Tx. Right? Current through Rx is I, right? Current through Rx is I. What was the value of I? We found at the first one. 1 ampere, right? 1 ampere. Then Px is 1 ampere, then 1 squared, and R is 10. R is 10. Then that is 10 watts. 10 watts. Then for Ry, we have to find the current through Y. Then total current is known, I2. I2 is known. I2 is 1 ampere. No? I2 is 1 ampere. And we know Ry and 10 are parallel. Ry and 10 are parallel. Right? Either you can apply current divider, right? Or else equate these potentials. V equals V. Right? Let's say current through this is simple line. Then there is 15 into simple line. Other side 10. Capital I was 1, no? 1 minus I. Then 15I equals 10 minus 10I. Then 25I equals 10. I equals 2 over 5. Then 0.4 amperes. I equals 0.4 amperes. Then a current of 0.4 flows through Ry. Then if you need Py is given by I squared R 0.4 squared. R is 15. Right, 0.4 squared is 0.16. No? Then 16 10 to the minus 2 into 15. 16 times 15 is 240, right? Yeah, then 2.4 watts. 2.4 watts. Then Pz, right? Pz, I of I through Rc is I3, no? I3 is also 1, then 1 squared times 6. That is 6 watts. 6 watts. Right? Then 8. Calculate the operating power of 12 volts and 4 volts batteries. Operating powers. Right. Powers of 12 volts and 4 volts batteries. 8. Then first for the 12 volts battery, I need the total current. Total current equals total current I total equals I1 plus capital I, no? Right? Then I1 was 2. I was 1. Then 3 amperes. That is 3 amperes. So we know P equals Vi. P equals Vi. Then V is 12. I is 3. Right? So that is 36 watts. 36 watts. And about the other battery, for 4 volts, again P equals Vi, right? And potential is 4. I through that is 1. Then 4 watts. 4 watts. Right? Calculate the operating power. Done. Right. Then part B. Consider the following responses happen simultaneously due to an emergency fire. Resistor Rs in the circuit is short circuited. Rs. Resistor Ry in the circuit is short circuited. Resistor Rc drops from 6 to 2. First one. Calculate currents I2 and I3 under these conditions using the expressions derived in A3 above. Right. If Rs is short circuit, if Rs is a short circuit, Rs Rs Rx or Rs Rs resistor Rs in the circuit and then resistor Ry in the circuit is short circuit. Okay, Ry is short circuit, which means no current flows through Ry. It's a short circuit. And Rx is a short circuit. Rs is a short circuit like this. Right? Then if Rs is a short circuit, there's no potential difference between A and B, no? Right? There's no potential difference between A and B. Then from the equation, right? I2 was VB plus 12, right? I2 was VB plus 12, right? Wait, I2. First we'll find I2, VB over 8, right? I2 is VB over 8. Then to find I2, if there's no current through this, then total resistance becomes 10 and 2, 10 and 2, 12. 10 and 2, it's 12. See, calculate the currents I2. Okay, first we need I2, only I2. Then I2 is go to the circuit again. Then from the circuit, if there's no potential difference here, VB becomes 12, right? If there's no potential difference here, VB becomes 12. Then 12 minus 0 over total potential, total resistance also 12. Then I2 becomes 1 ampere. I2 becomes 1 ampere, right? I2 becomes sorry, that's a short circuit. Wait. There's another short circuit here. No? Right now, if this is short circuit, then 10 ohms is also going to short circuit. 10 ohms is also going to short circuit. They are parallel. Then only 2 remains. Then 12 over 2, right? 6 amperes. 6 amperes. Then we need I3. It says R3 drops from 6 to 2. Right? Then I3 is, if VB is 12, this is also 12 now. Then potential difference 12 minus 0. Potential difference, 12 plus 4 over 6 plus 2, no? 6 plus 2. Then I3 equals 12 plus 4, 16, 8, then 2 amperes. Right? 2 amperes. 2 amperes. Right? Different conditions are given. Right? There's different conditions are given. Right? Repeat the same calculation under those conditions. Part 2. Right? I repeated the same calculation under the given condition. Part 2. Giving reasons, state what will happen. Burn or not burn to fuses F1, F2, and F3. Then we have to find currents. New currents. Now we know. Then new I1 is I1 was unchanged, right? I1 was unchanged, no? That was 1 ampere, right? Since I1 is 1 ampere, now ratings of fuses were given F1. Rating was 1 ampere, so it is not going to burn out, right? Then F1 is not burn out. F1 is not burn out. Then if you check I2, right? If you check I2, now I2 is 6 amperes. 6 amperes, right? Then for F2, only 5 amperes is withstandable. Then F2 is burn out. F2 is burn out since maximum current is exceeded. Since maximum current is exceeded, this is not burn out since maximum current is not exceeded, right? Then for I3, right? I3 was 2 amperes, no? Now new value of I3, 2 amperes, and this is also 2. Then I3 is 2 amperes. Then F3 is not burn out since maximum current is not exceeded, right? Not exceeded, right? Then okay, see, state how to find experimentally that the resistor RS in the above figure is short circuited using an ideal voltmeter. RS. If a resistor is short circuit, which means there's no potential difference across the resistor, no? Right? There's no potential difference across the resistor. Then if you are measuring it using an ideal voltmeter, have to connect the ideal voltmeter to A and B, and it should show a 0 reading. Right? Connect ideal voltmeter to A and B. and it should show a 0 reading, and it should show a 0 reading. Right, that's a normal question. Okay, first one is done. This is actually the last year question, 2025 last year question. And from the electricity questions, last year question is kind of an manageable and easier one, right? Last year one is kind of a manageable one. Manageable means kind of an easier one, the last year one, right? Next. Right. Next one. 24 question, 24, 2024 question, right? 24. Right, okay. No questions, right? Right, no questions, no? Right, we'll move on. 24. A thin heating element made from a conductive material of resistivity rho has a shape of a rectangular strip with a length L, width L, and thickness T, as shown in figure 1. First one. Write down an expression for the resistance R of heating element in terms of rho L WT. Right. So we know R equals rho L over A. Then rho L over area. Area, perpendicular area can be written as TW. Then rho L over TW. Right? Rho L over TW. Next. Then if L equals, okay, so calculate the resistance of the heating element. Okay. Then R equals, plug these values, rho is 8 times 10 to the power minus 5. Length is 100 millimeters 10 to the power minus 3 over W 20 T 5 micrometers. Then 5 micro 10 to the power minus 6 and W 20 milli 10 to the power minus 3. Right, then 10 to the power minus 3 to 10 to the power minus 3 cancels, 20 times 5, right, and 5 also cancels, then 80, right, 80 ohms, exactly 80, it cancels, and 80 ohms, 80 ohms, right. Then part B, as shown in the figure 2, a wearable heating pad is designed for localized heat therapy. Right, using the above thin heating elements, the heating elements are arranged as shown in the figure, along with a 40 ohm standard resistor. The pad is connected to a 24 volts DC source with a negligible internal resistance. Thin heating elements are represented by rectangles. Okay. Then the heating pad should produce at least 7 watts to deliver the required temperature, required therapeutic heat. Okay. First one. Calculate the resistance of branch AF and branch BE of the resistance of AF, right? Okay, now one such resistor was 80, no? Then RAF is they are in series combination 80 plus 80 plus 80. Then 240 ohms. Then we need RBE. RBE is 80 plus 40. That is 200 ohms. Right? Part 2. Calculate the current through the branch BE. Current through BE. Okay. If this is 24, right? If this is 24, these points are same, no? Since these points are same, see? Since these points are same, right? Potential difference across BE is also 24. Potential difference across BE is also 24. Right? Then for that branch, apply V equals IR. Then delta V equals IR This is for BE. Then this is BE. Right? Delta V BE is 24. And I need current. Calculate the current through BE. Okay. We need the current. I. R is 200. R is 200. Then 2 and 24 cancels, no? 12. Then 12 over 100. 12 over 100. 12 over 100 is 0.12 amperes. 0.12 amperes. Right? 0.12 amperes. Next, calculate the power dissipated in the branch BE. Power dissipated in the branch BE and the entire circuit. Does the heating pad produce the required power? Okay. Third, calculate the power dissipated in the branch BE. Okay. Then since current is known, we know power is given by I squared R. Then power of branch BE is, right, I squared is 0.12 squared. So we can write it as 12 times 10 to the minus 2 squared, and R is 200. 12 squared is 144. Then 10 to the minus 4 into 200. Right? Then these two cancels. 288 means 2.88, no? 2.88 watts. Right? 2.88 watts. Then since resistances of AF and CD are same, their powers are same, no? We can find their powers also. Then power of AF equals power of CD, because their potential differences are their resistances are equal and currents are also equal. Right? Currents are also equal. Right? Since current is not found, we'll go with the potential. Potential is known, no? We know we can write this as V squared dou R also. Power, we can write it as V squared dou R also. Now V is 24. Then 24 times 24 over resistance was 240. Then 24 times 10. That is 2.4 watts. That is 2.4 watts. PAF and PCD both equals to 2.4 watts. Then total power can be written as, right? Then P total. Then P total is power of AF branch plus power of BE branch plus power of CD branch. No? Then AF is 2.4. BE was 2.88. And this is also 2.4. Right? Then 2.4, 2.4, 4.8. Then 4.8, 6.8. That is 7.68, right? Then 7.68 watts. Right. Now it's asking whether it can produce the required power. Required power was 7, right? Required power was 7. Then write to your final answer. Yes, it can, since 7.68 watts is greater than 7 watts. Since 7.68 watts is greater than 7 watts. Right? Part 4. Part 4. Calculate the total power dissipation of the circuit if the thickness of all the heating elements is halved. Okay. If the thickness is halved, resistance becomes see, now what was the equation we proved? Right, we thickness equation R equals where is it? R equals rho L over dW. See, R equals rho L over TW. Now thickness is going to be halved. If thickness is halved, resistance is doubled. Right? If thickness is halved, resistance is doubled. Then the question is total power dissipation. Okay, if this is halved, then we have to find the new power. Then new resistance of BE. New resistance of BE is, say, RBE dash. Now, if resistance is doubled, 1 becomes 160 now. Right? 80 becomes 160. Then BE 160 plus 160 plus 160 plus 40. That is 360 ohms. No? That is 360 ohms. right? 360 ohms. Then new power here is power of BE, new value, say dash, right? Say dash. Now still potential difference is unchanged. Then we'll go with the potential difference, V squared over R. Then 24 times 24 over 360. 24 times 24 over 360, right? Then 12 times 2, 12 times 30. 6 times 4, 6 times 5. Then it becomes 1.6, right? Then this is 1.6 watts. 1.6 watts, right? 1.6 watts. And for other two, when resistance is doubled, right? When resistance is doubled, now new resistance of AF is, right? That is, previously it was 240, no? Now it is doubled. Then it becomes 480 ohms, right? Then powers are, so since potentials are, resistances are equal, power of AF equals power of CD, right? V squared over R, then 24 times 24, right? Over 480 now, over 480 now. Then 24, this is 20, then by 4, 6, and 5, then 1.2, no? 1.2 watts. 1.2 watts, right? Then new power is the V new, right? New power of AB plus new power of BE, right? AB name AF, new power of BE plus new power of CD. Then AB is 1.2 and PE was 1.6, right? 1.6 plus this is also 1.2. Then 1.2, 1.2, 2.4, then 4, right? 4 watts. New power of the system is 4 watts now. New power of the system becomes 4 watts. New power of the system becomes 4 watts now. Right. Then fifth one. If the length L is equal to the width W, show that the resistance is independent of the surface area LW of the heating element shown in figure. Okay, then resistance is, right, it goes rho L over TW. Now it says if the length is equal to W, if the length is equal to W, then rho L over, we can write this as TL. If length and these two equal, then it becomes rho over T. Right, that's a simple showing, rho over T. Right, this is independent of LW, independent of LW, right? Then right, so that, okay, we have shown 6. Calculate the resistance per unit square of the top surface of the above heating element having thickness 5 micrometers. Okay, then R equals rho over T, no? Rho was given before, 8 times 10 to the minus 5. Our thickness now is 5 micrometers, 10 to the minus 6. Then 16, right? 16 ohms. 16 ohms. Right? That part is done. Part C. Assume that a heating pad contains resistive elements made of two thin layers deposited on top of each other. Layer 1 made of a material with resistivity that remains constant with temperature. Right. Then something like this. Right. Layer 1 and layer 2. Right. Layer 2 made of a material with same resistivity as layer 1 initially, but resistivity increases as temperature increases. Okay. The heating pad operates using a constant voltage source. Giving reasons explain what will happen to the power dissipation of the modified heating pad over time. Okay. Check these two separately. What happens? Check these two separately. Resistance of layer 1 remains unchanged. Resistance of layer 1 remains unchanged, right? Then resistance of layer 2. Now with the time what happens is temperature increases, right? So with the time, over time, the impact is with the time temperature increases. When temperature increases, resistance increases. Resistance increases. Then resistance of layer 2 increases over time, right? Resistance of layer 2, we asked about resistance of power dissipation, power dissipation, okay. Then we can write about power at once, then power, not the resistance, power, right? So we know about power dissipation, right? Power. Then about power, that is opposite of the resistance, no? Right? Power you can't know, no? Because we know our equation is, right, about power. Power is given by, if potential difference is unchanged, V squared over R. Right? Potential difference is unchanged, V squared over R. Then when R increases, power decreases. Then power of layer 2 decreases with time. Decreases with time. Decreases with time. Right? And about total power also asked, right? Therefore, right? Therefore, total power. Now, total power is the addition of these two, no? Now, one decreases. Therefore, total power decreases with time. Total power decreases with time, right? A small explanation, right? You have to explain, right? Part D. A DC source to supply power to circuits can be constructed using a suitable step-down transformer here. A transformer is used to step down the input AC voltage of 240 RMS to an adjustable output AC voltage between 12 volts. Between 12 volts and 48 volts. Okay, between 12 volts and 48 volts. The transformer has 800 primary windings. At the output stage, the transformer output is converted to a DC voltage. Right, first one. Now it is connected to transformers, right? Transformers are initially coming from magnetic induction, right? Electromagnetic induction. Now this is connected to a transformer. Write down an expression for the ratio of primary voltage to secondary voltage of the transformer in terms of the number of windings in primary and the secondary. Okay. So that's a known equation of Vp over Vs equals Np over Ns. Right? Np over Ns. Equation of a transformer. Second one. If the RMS voltage of the secondary coil can be varied between 12 volts and 48 volts, calculate the range of number of windings required for the coil. Okay, then for 12 volts, first, if we find for 12 volts, then Vp over Vs, primary coil is 240, right? Primary coil is 240. Then 240 over 12 equals primary windings 800 over Np, right? Then simplify 0 to 0 cancels, 8 times 3 here, 8 times 10 here, then 3 times 4 here, then Np equals 40, right? 40 windings, 40 turns, 40 windings. Then for 48 volts, 240 over 48 equals 800 over Np again, right? Then 0 to 0 cancels, 8 times 3, 8 times 10. Then 3 times 16 here. Then in that case, Np equals 160. Then the range is asked, right? So therefore, the range of windings is, right, 40 to 160. Right? The range is 40 to 160. Range is 40 to 160. 40 to 160. Right. Part 3. Part 3. The DC output voltage is 80% of the RMS output voltage of the transformer secondary coil. If the desired fully rectified DC output voltage is 24 volts, calculate the output RMS voltage of the transformer. Right, then finally we need 24. 24 is only 80% of the RMS, no? Then V equals, right? V equals VRMS times 80%. 80% of this VRMS is here, right? Then VRMS is 24, right? VRMS is 24, no? VRMS is, sorry, V is 24. For the output voltage, 24, yeah. Then this is 24. Then this is 24. VDC is 24. VDC is 24. I need VRMS now, right? This is 0.8, no? 0.8. Then VRMS equals 24 over 0.8 means 8 over 10. Then like this, 8 over 10. 8 times 3, then it becomes 30 volts. It becomes 30 volts. Right now, 80% is utilized. Then RMS value needs it is 30 volts. Right? 4. That's the last, right? Yeah. Question 4. Question 4. The transformer supplies power to a load that consumes 120 watts at 24 DC. 24 DC. If the power loss due to joule heating in the secondary is 10%, okay, there's a heat loss now, there's a power loss of the power consumed by the load, calculate the RMS output current of the transformer, right? RMS output current. Then we know power is I know, then VRMS, IRMS, right? Power is VRMS, IRMS, right? And the total power is 120 watts, but there's a heat loss or power loss of 10%. Then total power consumed is 120. 10% loss means, right, 110%, right? 10% is lost. Then total power consumed here is 110. Then VRMS was 30. That we know, right? We need IRMS. Then this is 30 times 4, no? 30 times 4. 0 to 0 cancels off. Then IRMS equals 44 over 10. That is 4.4 amperes. 4.4 amperes. Right? 4.4 amperes. Right. The last part is a little bit a creative part. Last part is a bit creative part. Right? A bit creative part, and that's a good part. 24 question. Right? 2024. Right. Then we have to start 23. Okay, all good, right? Then next. A source X with 0 internal resistance is shown in figure 1. The voltage of X is linearly dependent on temperature and produces a current I from 0 to 20 milliamperes for the temperature ranging from 0 to 100. The current is linearly converted into a voltage between 0 and 5. Linearly converted into a voltage between 0 and 5. 5 volt range, and is measured across the resistor R as output voltage V. Okay, diagram is given, circuit diagram is given. Then A1. If R is an ohmic resistance, sketch the IV characteristics of R. Right? If ohmic, it follows V equals IR. Right? If ohmic, we know it follows Ohm's law. V equals IR. Then when we plot V and I, right? This is like V equals Ri, no? If you plot V and I, right? I is the x-axis, this is the gradient, this is the y-axis. That's a y equals mx. That's a y equals mx. Right. That's a y equals mx. Then, right, should be a straight line goes through center. Should be a straight line goes through center. Right? Y equals mx. Right. Then second one. Second one. Second one. What should be the value of resistance of the resistance R? What should be the value of the resistance R? Okay. Then maximum current it is going to flow is 20 milliamperes, no? And the maximum voltage is 5 volts. Then for R, delta V equals IR. Delta V is 5. Maximum current that is going to flow is 20 milliamperes. 20 10 to the minus 3 R. Then R equals, right, this is 5000 over 20. Then R equals 250, no? 250 ohms. R equals 250 ohms, right? 250 ohms. Next, part 3. Calculate the values of voltage and current across the resistor when the temperature of X is 25 degrees Celsius. Hence, find the power dissipation in the resistor. Okay. Calculate the values of voltage and current. Okay, it says the voltage changes linearly, no? Voltage changes linearly, which means voltage and temperature are linearly changing from 0 to 100, right? It is like this. Then when temperature varies from 0 to 100, voltage varies from 0 to 5. Then if temperature is 1/4, voltage should be 1/4. Then new voltage is 5 over 4, 1.25 volts. New voltage is 1.25 volts. It follows the same ratio. It should follow the same ratio. Right. Then voltage and the current. Right. Then the new current is right. New current is new current. Now voltage is at 1.25 across this one, no? 1.25 across here R. Then to find new current again for R, delta V equals IR. Now delta V is 1.25, right? And I need new current, say I dash, and R is unchanged, 250. R is unchanged, 250. Then I dash equals, right, 1.25 over 250. 1.25 over 250. Then if this shows 125, this is 2, no? Then this is 0.02. 1 or 0.02. 1 or 0.02 means 5 times 10 to the power 3. 5 times 10 to the power minus 3. Right? Then current is 5 milliamperes. Current is 5 milliamperes. 5 milliamperes. Right? And hence find the power dissipation in the resistor. Okay. Right? Not over yet. Right? Now the power dissipation. Then power dissipation of the resistor is given by, if the current is known, I squared R. Power dissipation is given by I squared R. If current is known, then I squared is 5 times 10 to the power minus 3 squared. R is 250. R is 250. Then 5 squared is 25. This is 10 to the power minus 6, right? 10 to the power minus 6 times 250. 25 times 25 is 625, no? Then this is 625. Then 0 10 to the power minus 6. Then we can keep it as 6.25 10 to the power minus 3 watts. So that is 6.25 milliwatts. 6.25 milliwatts. 6.25 milliwatts. That part is done. 6.25 milliwatts. Right? Part B. Part B. Suppose that resistance R1 is connected parallel to X and the wire segment BC. R1 okay, is shown wire segment BC, and the wire segment BC in the circuit shown in figure 1 is replaced by a resistor R2 as shown in the figure 2. Okay, let R remains constant at the value calculated in A2 above. That was 250. Right, first one. When the source produces a voltage Vs, right, Vs here, Vs, write down an expression for the current I passing through resistor R. Okay, when the source produces Vs, okay, then right, if the source produces Vs, right, right, we know this Vs is between A and B, no, which means VAB equals Vs. Because that is between A and B. And total resistance, now this same I flows to this, no? Can you see that these two resistors are in a series combination? Right? Which two? R2 and R. R2 and R in a series combination. And they are seriously connected between A and B. Right? They are series between A and B. Then what we need is current, no? Then apply delta V equals IR. IR for the branch AB or BA. AB. For the branch AB or BA or BA. Right? For the branch AB. Right? Then R AB. Delta VAB is Vs. Right? I need I. And total potential from A to B is right, that is actually BA. Current flows in the opposite direction, no? Then these two should be BA. Current flows in opposite direction. Right, then BA, right, and B A. See? Right, then RBA is R2 plus R, no? R2 plus R. Then Vs equals I times R2 plus R is 250. Now we need I. I equals Vs over R2 plus 250. Right? See, I is this. Now I is known. Right? Then part 2. Right? Part 2. Hence, write down an expression for the source current Is. Okay. Then Is is the addition of Is is the sum of these two currents. Now let's assume the current flows here as simple line. Right? Now first I can find simple line. For R1. See, for R1, apply delta V equals IR. For R1, delta V equals IR. Then delta V is Vs, no? Equals current is simple line R1. See, now simple line is known. That is VSO R1. Now, I know Is has divided into 2. Since Is has divided into 2, right? See, now be with the question from the beginning. Always when you do essays, it has a nice flow. Right? Always it has a nice flow. Right? We have to always be in the question, be with the focus in the question from the beginning, right? When you are going in that flow, then IS is the addition of I plus simple I. Then capital I was Vs over R2 plus this thing, no, right? So that is Vs over R2 plus 250 plus simple I was Vs over R1. Then this is IS. This is IS, right? This is IS. Hence, write down an expression for the IS. Okay, expression is here. Then IS is given by this. Expression is here. Part 3. Part 3, right? These are the 3 most recent electricity questions that has been there, right? Most recent electricity questions, right? Part 3, using the expression B1 and B2 above, state what will happen to the ratio IS to I if R1 is very greater than, extremely greater than R plus R2. What is the physical significance of this? Physical significance, okay. Then we have 2 equations for I and IS, no? Yeah, we have 2 equations for I and IS. Then let's divide these two. We need IS over I. Then IS is, see, IS equation. For IS equation, if you apply a common denominator, it is R1 times R1 plus 250, right? And the top becomes Vs R1, right? No, Vs is common, no? Let's take it out. Vs is common. If Vs is out, then R1 plus R2 plus 250 comes here, right? So this is equation 1, right? And for I we have Vs over R2 plus 250. I is Vs over R2 plus so R1 plus R2, ne? Then R1 no R2, this is R2, right? I'm gonna make R2, this is R2, right? Then R2 plus 250. Say this is equation 2, right? Now divide these two. We need ISO I. Divide these two. See what happens. Then IS over I, that is 1 over 2 from my equations. 1 over 2, right? 1 over 2. Then ISO I equals from IS Vs times R1 plus R2 plus 250. R1 plus R2 plus 250 over R1 times R2 plus 250. R1 times R2 plus 250 over I, then it becomes a reciprocal. Then here it becomes R2 plus 250 over Vs, right? 250, yeah? 250 over Vs, right? Now, see what happens. Vs cancels. R2 plus 252, R2 plus 250 cancels. Then ISO I becomes, right? ISO I becomes R1 plus R2 plus 250 over R1. Right. Now, what is the given condition? R1 is greater than R plus R2. Then let's convert this to R. That is easy to compare. No? 250 is R. No? 250 was given as R. Then R1 plus, this is R2 plus R. R2 plus R. R2 plus R. R2 plus R over R1. Right. See what happens now when this is extremely greater. Right. When this is extremely greater, when R1 is extremely greater than this one, right? This addition goes to, right? If this is negligible, if this part is negligible with respect to R1, R1 goes to R1, no? This addition goes to R1, no? Right? If that is extremely greater, then denominator that is also R1, then it becomes 1. Then what is our final output? Final result is, then IS over I becomes 1. IS over I becomes 1 in that case. IS over I becomes 1, right? Then the question is, what happened to the ratio? It reaches 1, right? It's equals to 1, right? It equals to 1. And what is the physical significance of this? Is to I equals 1 means, now what's happening from this is is equals I, no? When is equals I. Now if is equals I, this simple I becomes 0. Simple I becomes 0. Then what happens is, hence, 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 simple I becomes 0. Then physically what happens is, if simple I becomes 0, right, there's no current flows through, right? There's no current flows through R1, no? There's no current flows through R1. Then physically what happens is, I equals 0, then no current flows, no current flows, no current flows through R1. No current flows through, no current flows through R1. Right, then physically, this is what is happening. No current flows through R1. Right, see, that's a beautiful flow. Right, that was a nice and beautiful flow. Today also, will you be discussing only 3 essays? In this Tute, I have put only 3 essays, right? 25, 24, and 23 essays, right? 3 past papers. Okay, right? That was a good part, huh? That was a good part. Then, moving on, part C. Part C. C to which that is linked to, right? Part C. In a computer hard disk drive, HDD data is stored. HDD data is stored by magnetizing tiny regions of a thin film deposited on a flat circular disk, as shown in the figure 3. A cylindrical rod passing through the axis of the disk is used to spin the disk. When the disk spins, the information stored in the disk is read as an induced EMF. Right. Now it is going to link to magnetic induction. Right. Magnetic induction again, induced EMF generated in the read-write head, which is a conducting read-write head, which is a conducting horizontal square loop of side length d placed just above the disk. The disk is spinning with a constant angular velocity omega. Right. When located at mean distance r from the center of the disk, passes under the conducting loop where r is very greater than d. The magnetic region produces a uniform magnetic field of flux density B, pointing upwards, right? Pointing upwards. An enlarged picture of the square loop seen from the above is shown in figure 4. Okay, this one, right? An aerial view is given, that is clear. Aerial view is clear, right? When the magnetic region is completely underneath the loop, the magnetic field produced by the magnetic region is directed out of the plane of the loop. Okay, first one. Sketch the variation of induced EMF psi with time t as follows. Psi with time t as follows. T1 T1 as the time when the field just enters the loop. Field just enters the loop. Okay. Then we know E is, right? We need to plot induced EMF, right? E is minus delta band over t, no? Or this is also written as minus d phi by dt. Delta band over t or d phi by dt. Right? Now when it enters, what changes is only delta A over t. Then this is proportional to delta A over t. This is proportional to delta A over t. Right? Then if we plot a time variation, right? Induced EMF is given as psi now. It is given as psi now, right? And let's say time starts from here, t1, t2, t3. Then as a time when enters the loop, okay, say then t1 is here, right? T2 when the loop is fully inside, then t2 and T3, right? So we know when it enters, delta A changes. When it enters, delta A changes. When delta A changes, there is an induced EMF, right? Since delta A, change of delta A is constant, right? We have drawn these variations in the class, right? We have drawn these variations in the class. Then let's split these intervals for the clarity. Then from T1 to T2, there is an induced EMF like this. Then T2, as the time when loop is fully inside. Fully inside means there's no change. If there is fully inside, no change of area. No change of area means this is 0. It becomes 0, right? And when it leaves, we know according to Lenz's law, right? Always, according to Lenz's law, when enters and exits, always directions of EMFs are opposite. Don't check again and again because that's how it works from Lenz's law, right? Then from T3, again, it should be same magnitude but opposite direction. Then the final variation we are getting is this. The final variation we are getting is this, right? Final variation is this, right? And in terms of these heights, they should be equal, right? If this is E, this is minus C. Same magnitude, opposite directions, right? The reason is Lenz's law, right? What causes the opposite direction is Lenz's law, right? Part 2. Write down an expression for the magnetic flux phi through the square loop in terms of B and D when the loop is completely within the magnetic region. Okay, then we know phi. Phi is written as band, no? Equation of phi is band. Then B is given as B. And area of this loop is side length is D, no? If side length is D, area is D squared. Number of turns, only 1. Then phi equals BD squared. Right? It is done. Part 3. Write down an expression for the time delta t taken for the magnetic region to pass the loop in terms of d, r, and omega. Assume that the magnetic region is at a mean distance r from the center of the disk. Okay. Right. Time it takes to pass. Then in terms of d. Okay. Then we know s equals ut. Then to pass a distance d, right? If the time takes is delta t, right? This is what happens. Now, if there is at a distance r from this loop, right? Now from this loop, there is at a distance r. So we know speed of a particle here or speed of the disk here is given by r omega. No? Speed is given by r omega at that point. If there is at a distance r, then d equals u is r omega, right? Because we know v equals r omega. Then r omega delta t, right? We need to write the expression for delta t. Then delta t is given by d over r omega. Right? It is linked to circular motion also. Right? Circular motion also link. Right? Nice flow. Right? Starting from Ohm's law, then normal electricity, right? Ohm's law, electricity, equivalent resistance, right? Power calculations, power dissipation, and then electromagnetic induction, and now circular motion, a touch of circular motion, and so on. Right, part 4 then. 4. Using your answers to part C2 and C3 above, or otherwise, write down an expression for the magnitude of the induced EMF psi of the loop in terms of BDR omega. Right, we know E is written as, right, d phi over dt, no? d phi over dt, right? Then E is given as psi here, that is written as d phi over dt. Then d phi over dt is, right, difference of phi over difference of t. Difference of phi over difference of t. Then this is delta phi over delta t. Then delta phi is, for phi we proved something, bd squared. Then that is bd squared over delta t is d over r omega. Then d over r omega goes here reciprocal. 1D cancels. Then this equals BdR omega. BdR omega. BdR omega. BdR omega. Right? Still we are in that nice flow. Still we are in that same nice flow. BdR omega. Right? Then 5. Taking towards a calculation. Taking towards a calculation now. Taking towards a calculation now. 5. The area of the circular disc with the radius of 62.5 millimeters is half filled with 1 times 10 to the power minus 10 to the power 13 isolated uniformly distributed square magnetic regions. Okay, square magnetic regions. Right. Now this one was a square magnetic region. Right. This one was the square loop, square magnetic region. Right. Such 10 to the power 13 are there. Such 10 to the power 13 are there. There are no magnetic regions in the cylindrical rod of radius 12.5. Okay, see, this part is a cylindrical rod, no? This part is a cylindrical rod. No magnetic field here. No magnetic field here. Then magnetic field is only in the remaining disk, right? Magnetic field is only in this darkened volume. Magnetic field is only in this darkened volume, right? Magnetic field is only in this darkened volume only, right? That is only in this darkened volume, right? Then radius or radii are given to us to find, and there's no magnetic field here in the cylindrical part, cylindrical rod. Okay, then calculate the side length d of a single magnetic region. Side length d of a single magnetic region. Take 5 equals 3 and root 562.5 is 24. Okay, a root is given. Then in the calculation, definitely we must get this value. Right, in the calculation, we must get this value. Okay. Then right, then if we write total magnetic field or the total area of magnetic field, total area of the magnetic field, right? Total area of magnetic field, right? Phi, from the larger circle, we have to subtract the small circle. No, small circle means rod, right? Rod subtract then it is 62.5 in millimeters. In millimeters minus 12.5 squared. This in millimeters, right? In millimeters, then 10 to the power minus 6, right? 10 to the power minus 6. 10 to the power minus 6. Then at the same time, we can write the total area of the magnetic field using this. No, now one side here is, right, one, what we call the square loop here is of side length d, right? And such 10 to the power 13 parts are there, right? Such 10 to the power 13 parts are there. And another important data was given, that is half filled. That is half filled. Then this area is not this, right? Then this area is not this. This is over 2. That is half filled. That is important. That is half filled. That is half filled. Then only a half of this area. Only a half from this area. Then using this, we can write using these ones, the squares, we can write the area again as there are such 10 to the power 13 parts, isolated, what they call them, square magnetic regions inside. No, then total area of that is, right, area of one such is d squared, and there are such 10 to the power 13, and there are such 10 to the power 13. Then this equals this. No, this is 3, right? This is 3. Then we have to simplify this now. 62.5 squared, right? Now that's a simplification. 62.5 and 12.5. 12.5 is common, right? 12.5 is common. Then when we simplify manually, right, if you see that 12.5 is common, or else we can write a square of 2. Yeah, that's better. This is the square of 2, square of a difference. No, then we can write this as 62.5 plus 12.5 times This is 62.5 minus 62.5 minus 12.5 minus 12.5, right? Then 10 to the power minus 6 over 2, right? Then this is d squared. This is simplification now. D squared 10 to the power 13, right, equals 3 times, right? 62.5 plus 12.5 means 62.5, 72.5, 75, right? That is 75, right? Times this is 50, 10 to the power minus 6 over 2, right? Then keep simplifying until we get the answer, and that given hint should also be coming somewhere, right? Given hint should also be coming somewhere. Then this is 2 times 25, right? Now 75 times 75 is coming now, right? Now finally what I have here is d squared 10 to the power 13, and this side 75 times 75, 10 to the power minus 6. Then check the value of 75 times 75, right? So I guess it should be that given value, 75 times 75. Yeah, that is exactly that, 5625, right? Then 5675, right? Which means d squared 10 to the power 13 equals 5625 10 to the power minus 6, right? We need d now. Then d squared equals 5625 times 10 to the power minus 19. 10 to the power minus 19. Now the given value is 562.5. Then rearrange this as now it's a simplification. 562.5 can be written as 10 to the power minus 18, right? 10 to the power minus 18. Then this square root is given. Now d is square root of this 562.5, and square root of 10 to the power minus 18 is 10 to the power minus 9. This value is given. Then this is 24 times 10 to the power minus 9, right? See how nicely it's coming. Then 24 10 to the power minus 9, right? 10 to the minus 9. Minus 9 means millimicro nano, right? Then we can keep it as 24 nanometers. 24 nanometers, right? 24 nanometers, right? Nice calculation. 6. If B equals 10 to the minus 3 Tesla and the angular speed of the spinning disk is 540 radians per second, calculate the induced EMF psi on the loop when the magnetic region situated at the circumference R equals 62.5 millimeters of the disk passes under the loop. Right, for psi we have proved an equation before. Then psi can be written as, what was the equation we proved? Psi is BD R omega. Psi is BD R omega. Psi is BD R omega. Then B is given 10 to the power minus 3, right? And D we found 24 nanometers, no? 10 to the power minus 9. Radius 62.5, but in millimeters, then 62.5 milli 10 to the power minus 3. Omega 540. Omega 540, right? Again a simplification. Right? Then the numbers are 24 times 62.5 times 54, and remaining 10 to the powers are minus 3, minus 9, minus 12, minus 12, minus 3, minus 15. Then with this 10 to the power minus 14, right? Then this should be simplified, right? 24 times 54 times 62.5, that is 81,000. Then this is 81,000 10 to the power minus 14, right? Keep it in the simplest form. Right? Keep it in the simplest form. then it can be written as 8.1 times, right? 8.1 times 10 to the power minus 10, no? Right? 8.1 times 10 to the power minus 10, 10 to the power minus 10 volts, right? So if needed, we can give it in nano. Then this is 0.81 times 10 to the power minus 9 volts, no? 10 to the power minus 9 is nano, then 0.81 nano volts. 0.81 nanovolts, right? That's it. Right? That's also a nice question with a good flow, with a nice flow, right? So what I discussed today was most recent last 3 questions, last 3 years questions, right? Then with that we have come to the end. Any questions? Any questions or anything to clarify? Any questions? Is it clear enough? Okay, right. Then if no questions, right? If no questions, we can wind up, right? So remaining again, we are 10 days from the exam, right? We are 10 days from the exam. So it's the golden era or the golden days passing on now, right? So whatever you did in the previous days, on the previous days, right? Now what is going to count here is, right? What is going to count here is the last days, because always in anything, right? The way we end something matters, and that is what is seen by the people. That is what is seen by the outsiders, right? They don't know how we started. They don't know how we went through. They don't know how we went through in the journey of these 2 years and 2 months. That they don't know, right? The only thing the outsiders know is, right, once results are issued, then when you say 3A's, 2A's, 1B, so likewise, that is what they see. That is what they see, right? They see only the output, right? Then to go to your that final target and the expected output, right? These days are the golden days now. These days are the golden days, because whatever you did in the previous days, right? Now totally depends on, relies on what we do in these days, right? Because මොනා කරලා තිබ්බත් කලින් දවස් ටිකේ මේ දවස් ටිකේ හරියට වැඩේ කරගත්තේ නැත්නම් ආයෙමත් ඔයාලට අර expected results එන්නේ, right? That's the thing. That's the thing. So spend your time wisely and manage everything wisely, right? And yeah, in the theory class I gave you a schedule for these coming 24 days also, right? Coming 24 days until you finish the exam, right? I gave you the schedule, and I'll share the schedule again in the next paper class, right? On Monday we'll share the schedule again, right? And some other paper discussions and essay discussions, and those such discussions will take place in the coming days also. So stay in touch and manage your time, right? Manage your time. Stay safe and healthy, because even if you got a headache, last day also I told you, even if you got a headache these days, it matters a lot. Right? So therefore stay healthy and keep up the good work. All right, then if no questions, we'll wind up. See you in the next session or next class, right? Good night and goodbye. See you.